Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Dedarendi Pauji and my student ID number is 24030400040. In this video, I will discuss a topic about storage, specifically the hard disk drive. This video is created to fulfill an assignment for my English course. Let's get straight to the main topic. What is a hard disk drive? A hard disk drive is a data storage device that uses spinning magnetic disks to read and write data. It consists of key components such as magnetic platters, a read or write head, and a motor that enables the platters to spin at high speeds. Data is stored in bits on the surface of the platters, organized into sectors and tracks. Hard disk drives are widely used in computers, laptops, and external storage devices to store various types of data, including operating system, application, documents, photos, videos, and other files. Although hard disk drives offer large storage capacity at a relatively low cost, their performance is lower compared to solid-state drive because data reading and writing depend on mechanical movements. However, hard disk drives remain popular due to their affordability for storing large amounts of data. To better understand how a hard disk drive works, let's take a look at an animation from Branch Education that explains it in more detail. Imagine every picture you took over the past year, all saved within the area of a single dot of ink from a ballpoint pen. Well, this is approximately how compact data is stored inside a hard disk drive. And in this video, we're going to open one up and see how an entire library worth of book is able to fit within the surface of this metal disk. We'll start by opening up this hard drive and detailing the components inside. After that, we'll dive into exactly how the drive stores data using the read and write head, and in the process, we'll look at the tracks, sector, and magnetic domains of the metal disk. Finally, we'll explore some of the latest advances that enable over a terabyte of data to fit within every square inch of the disk. The inside of this drive, we find a variety of components. Here's the disk or platter that stores all the data, and depending on the storage capacity of the drive, might be multiple platters installed. The disk is composed of an aluminum-magnesium alloy with multiple coating of the other alloy, but the magnetic functional layer is this 120 nanometer thin layer of a cobalt-chromium titanium alloy, which has small magnetic domains or regions whose direction can be manipulated via external magnetic fields. The platter is mounted on a spindle with spin at a speed of 70 to 100 rpm, using a brushless DC motor at its center. Next, there's a headstock assembly, with one arm above and one arm below each disc, and with a slider and a right head at the end of each arm. The slider is uniquely designed, such that it catches the airflow generated by the ludicrously fast spinning disc, and uses the airflow to float or fly the right head, so that is only 15 nanometers or about 100 atoms away from the surface of the disc. For reference, here's the thickness of a sheet of aluminum foil. Because the arm assembly flies on top of the spinning disc, it's only broke over the surface when it's at full speed. And when the disc is not spinning, the arm assembly is parked to the side on a small piece of plastic. Back here, a voice coil motor composed of a coil of wire and two strong neodymium magnets above and below. It's used to move the entire arm stack assembly. When electric current is run through the coil, it creates an electromagnet, which is influenced by the neodymium magnets, thus generating a force that causes the arm to move across the disc. When a reverse current is sent through the voice coil, the arm is forced in the opposite direction, thereby enabling control of the exact position of the read-write head within 30 or so nanometers. Additionally, the magnet and voice coil make a rather strong motor that enable the lightweight arm stack assembly and read-write head to move back and forth to different tracks across the platter, up to 20 times a second, and to make small adjustments incredibly fast. In order to connect to the read-write head, a flexible ribbon of wire is routed along the side of the arm and down to this connector, which feeds signal to the outside of the hard drive enclosure and to the printed circuit board or PCB. On the PCB, we have the main processor as well as a DRAM chip, which is used as a scratch bus for the processor and a buffer for the incoming and outgoing data. Additionally, mounted on the PCB is a chip for controlling the voice coil and brushless DC spindle motor, and then on the edge of the PCB is a SATA connector which connects to the motherboard for communication and a separate connector which goes to the power supply. Additional important components are the gasket that seal the disc from the exterior environment and two filters that catch any stray dust particle. These filters are necessary since the read-write heads are just 15 nanometers away from the platters, and a single dust particle can be up to 10,000 nanometers large, and could cause major damage if it were to collide with the 7200 RPM disc. Now that we look through many of these components, let's see how they work. To begin, the disc is divided into a concentric circle of tracks. The latter hard drive can have more than 500,000 tracks on just one side. These tracks are then divided into sectors, and in each sector is a preamble or synchronization zone, which tells the read-write head the exact speed of the spinning disk and the length of each bit of data. The next part of the sector is the address, which helps the read-write head know which track and sector is currently positioned. After that, we have the actual data that's stored, typically 4 kilobytes of data per sector. Next is an area for an error correcting code, or ECC, which is used to verify that the data stored in the block is accurately written and properly read. And finally, there's a gap between this sector and the next, which allows the read-write head some tolerance when reading the contents of a block. Now, let's zoom in on the read-write head and the disk to see exactly how data is written and read. Writing data to the disk is done by manipulating the direction of magnetization of a localized region or domain of the cobalt chromium titanium layer in the disk, and forcing the region to be magnetized in the up direction or the down direction. This tiny magnetic domain or region is around 90 by 100 by 125 nanometers, and when magnetized, all the atoms will have their even thinner magnetic north-south force pointing in the same direction in order to magnetize a single domain, which is equivalent to writing a single bit of data. A current is applied to a coil of wire at the back of the write head, thus creating a strong magnetic field back here. The magnetic field is channeled through the write head and focused into a small point at the tip, and then jumps across the 15 nanometers air gap and into the disk. When the focused magnetic field passes into a single domain of cobalt chromium tantalum, all these atoms are forced to align their tiny atomic magnetic fields with the applied magnetic field from the write head, thus turning the small domain or region into a permanent magnet. The key is that even when the write head is moved away, the direction of the magnetic domain in this layer of the disk is maintained for years, and they emit a permanent magnetic field which can be repeatedly sensed by the read head every time you read out the data stored in this sector. That is, of course, until the computer and write head rewrite a new bit of data to the domain by either flipping the direction or keeping it the same. Let's explore how we read data from the disk. Thus far, we've been showing domain as pointing up as a binary 1 and pointing down as a 0. While this is conceptually simple, it isn't actually the case. Rather, the red hat is designed to detect the change in orientation from magnetic domains pointing in one direction, and then the adjacent domain pointing in the opposite direction. This is because emitted magnetic field from adjacent regions that switch their orientation are much stronger than the emitted field from just a single domain, pointing one direction or the other. Therefore, each change in magnetic domain pointing in one direction to the opposite direction is assigned a 1, and an absence of a transition from one domain to the next is assigned a 0. Therefore, the right hand will record a binary sequence of 0011, 0010 like this, or a sequence of 1101, 1110 like this, where the ones are changed and the 0 are lack of change. So then, what inside the red hat that detects these magnetic fields? Well, inside is a multi-layer conductive material composed of an alternating layer of ferromagnetic and non-magnetic materials. This multi-layer material has a property called giant magnetoresistance or GMR. And put simply, it's a material that changes its resistivity depending on the strength of magnetic field that passes through it. Therefore, using GMR is a simple matter of just measuring the resistivity. And when there is a low resistivity, that means there are strong magnetic fields below the red hat resulting for a change in domain orientation, and it's a 1. And when there high resistivity and no change, it's a 0. However, this poses the problem of how a string of dozens of not changing domain can result in an ambiguous number of zeros. To fix this, in each sector, the preamble is simply a set of alternating domains and is used to set the size of each domain. And then the error correcting code at the back of the sector is used to ensure no data is lost. Next, we're going to explore some advances in hard disk drive technology that improve the areal density, which is the number of bits that can fit within a given area. In this graph, you can see how areal density has increased by over 50 million times throughout the past 60 years. However, perhaps more important is that the cost to store trillions of bits of data has dropped. Just imagine, if we were to time travel this hard drive back to the 1960s, it would be worth over $4 billion. And now in 2024, it costs less than $40 and is far faster and more reliable than the disk drive from the 60s. Let's now return to hard drives and see some of the advances that allow this disk to store terabytes of data. First, around 2010, the orientation of the domain was switched from being horizontal to vertical, and with it the white and red hat also had to change their orientation. This change in orientation is due to the fact that as a magnetic domain shrinks in volume, it becomes more easily affected by temperature. So, by changing the orientation to vertical, the domains or magnetic regions can utilize the depth of the material while continuing to shrink the area on the disk that each domain takes up. The next advance we're going to look into is called Single Magnetic Recording or SMR, which started being commercially available around 2020. Before single magnetic recording, hard drives typically used the technique classical magnetic recording or CMR, where the chunk of data are 90 nanometers wide and have guard bands on either side of the track. However, with single recording, the tracks are written to partially overlap with previously written tracks, with no guard bands to separate each track. Thus, we can fit many more tracks and much more data into a given area. Note that the red hat is much smaller than the white hat, and as a result, one single track can be reliably read at a time. This issue, however, is that if you were over a track and the upper track of single data is still good or valid data, the drive will first have to read and store the valid data in the DRAM buffer and write both the lower track of new data and the upper track of valid data. And as a result, the buffering and the extra read and write step can result in a loss of performance. The third advance we're going to discuss is heat-assisted magnetic recording or HAMR, which is not yet commercially available. Essentially, this technology utilizes a small, focused laser to hit the region that is actively being written to. By hitting the domain, the magnetic region can be more easily influenced or coerced to orient in a particular direction. This is necessary because both the write head and the localized electromagnetic field are incredibly small, and by making the magnetic region more easily coerced using focused heat, we can continue to shrink the size of the magnetic domains.